Welcome to another open learning session where I'm going to catch up with deep learning. I'm using this book called Mathematics of Machine Learning, and today we are looking at the chapter 2.5, Linear Independence. In the following, we will have a close look at what we can do with vectors. In particular, we can add vectors together and multiply them with scalars. The closure property guarantees that we end up with another vector of the same in the same vector space. It is possible to find a set of vectors with which we can represent every vector in the vector space by adding them together and scaling them. This set of vectors is a basis, and we will discuss them in section 2.61. Before we get there, we will need to introduce the concept of linear combinations and linear independence. Okay, so what they're saying is we can build vectors of other vectors, and there's a special set called basis. If we have them, we can build basically every vector within that vector space. Definition 2.11, linear combination. Consider a vector space V and a finite number of vectors, then every vector of the form, this form, with some lambdas is a linear combination of the vectors 1 to k. Okay, so what they're saying is they have a number of vectors and they add them together. And so you can think of, so let's say you have one vector and another vector and another vector and another vector and so on, yeah? And another vector. And you basically add all these vectors together. You will end up with a new vector, something like that. Now you can scale each vector. Like each vector can be scaled. And now what you have is now you have like, okay, let's say the scalars, they are variables. Now you will not end up with one single vector. Let's put this red. You will end up with like a bunch of vectors. Sometimes it's also the orientation is different and so on. So you will have a set of vectors which you can end up with just by having different scalars. Yeah, okay. In this example, we have the vectors fixed, and what we say is the red vectors, they are a linear combination of these vectors and these scalars. That does not necessarily mean that we will reach or can construct every vector. It just means that you can take a bunch of inputs as vectors and scalars and have an output, a bunch of other vectors. That's all they are saying here. Okay, so the next sentence, the null vector can always be written as the linear combination of k vectors because the null vector is always the sum of if you scale it to 0, right? So they take whatever vector you have and you just scale it down. And that's always true. In the following, we are interested in non-trivial linear combinations of a set of vectors to represent null vector. For example, linear combinations of vectors where not all coefficients are 0. The coefficients, at least not all of them, should be 0. Then it's getting more tricky. Okay, so definition 2.12, linear independence. Let us consider a vector space V with k as a number and x1 to k are vectors. If there is a non-trivial linear combination such that the null vector equals to, like, adding these, basically, let's just call it linear combination. Okay, let's read the sentence better again. If there is a non-trivial linear combination such that the null vector is a linear combination with at least one lambda is not 0, the vectors are linear independent. If only the trivial solution exists, so only the solution exists where all the lambdas has to be 0, the vectors are linear dependent. Okay, so this term linear dependency is equal to, can you get the null vector without a 0 in lambda as a scalar? And that makes sense. Like, in my head it makes sense. Let us read a bit more and then I will try to add my explanation. Linear independence is only of the most no, wait. Linear independence is one of the most important concepts in linear algebra. Intuitively, a set of linear independent vectors consists of vectors that have no redundancy. If we remove any of those vectors from the set, we will lose something. Throughout the next sections, we will formalize this intuition more. Okay, let's try to explain a bit more here. So what they're saying is, let's say you want a null vector. A null vector is basically just zeros. You have the vector 1, 0 and 0, 1. Okay, so basically it's not possible for us to get to this null vector except lambda being 0 and lambda 2 being 0. There's a plus missing in the middle. In case we have, for example, 1, 2 and 5, 3. In that case, you could argue that there is a lambda 1 and a lambda 2, which is not 0, which you can set to make this equation work. So of course lambda 1 is here and lambda 2 is here, the two scalars. And this is what they basically mean with independence. It is independent if the only solution to this equation is lambda 1, 2, and so on being 0. Okay, let's move on. Example 2.13, linearly dependent vectors. A geographic example may help to clarify the concept of linear independence. A person in Nairobi describing where Kigali and Rwanda might say, you can get to Kigali by first going 506 kilometers northwest to Kampala and then 374 kilometers southwest. This is sufficient information to describe the location of Kigali because the geographic coordinate system may be considered a two-dimensional vector space. The person may add it is about 751 kilometers west of here. Although this last sentence is true, it is not necessary to find Kigali given the previous information. Okay, so what they're saying basically is there are vectors and you have these points. These cities are points and you can connect them. And going first using the blue vector first, and then the purple one is the same as doing just the third one. And actually we can see that if you just do the vector addition, it will be the same. Okay, let's finish the reading. In this example, 506 kilometers northwest, the blue one, and the purple one are linearly independent. This means the southwest vector cannot be described in terms of the northwest vector and vice versa. However, the third vector is a linear combination of the two vectors, and it makes the set of vectors linearly dependent. Yes, because we do addition, right? Equivalently, given 751 kilometers west and 374 kilometers southwest can be linearly combined to obtain 506 kilometer northwest. You can do basically a subtraction, is what they're saying. The following properties are useful to find out whether vectors are linearly dependent. K vectors are either linearly dependent or linearly independent. There is no third option. Okay, it's an or. If at least one of the vectors is a null vector, or two vectors are identical, they are linearly dependent. The vectors 1 to k, where none of them are null vectors, and k is, what is this? Greater than 2? Okay, they are linearly dependent if and only if at least one of them is a linear combination of the others. In particular, if one vector is a multiple of another vector, basically you scale one up and down and then you have it twice, then the set is linearly dependent. They are linearly dependent if they are a linear combination. So basically they mean that you can construct one of those vectors by taking two others, or if you scale one. A practical way of checking whether vector 1 to k are linearly independent is to use the Gaussian elimination. Checking if they are independent, use the Gaussian elimination. Write all vectors as columns of a matrix A and perform Gaussian elimination until the matrix is in row echelon form. Basically the staircase thing. The reduced one, where you only have pivots of 1 and everything else is 0, is not necessary. The pivot columns indicate the vectors which are linearly independent of the vectors on the left. Note that there is no ordering of vectors when the matrix is built. So in the beginning there is no ordering, but once you do the Gaussian elimination, you will naturally order them. And then you push dependence to the right and from each pivot, and independence to the left. That makes sense. The non-pivot columns can be expressed as linear combinations of the pivot columns to the left. For example, in this version, you will have that one. You can say, okay, this one is linear independent, but that one is not, because it is basically a scaled up version. And that one is linear independent to both of those to the left, because the 2 only has zeros on the left. So there's no way you can construct them by like adding or scaling. And to conclude, yes, all columns are linearly independent if and only if all columns are pivot columns. That makes sense. Okay, next example, 2.14. Consider R4 with three vectors. To check whether they are linearly independent, we can follow the general approach and solve this equation to be 0. So they will write the matrix and then they will do the Gaussian elimination. And we can see that every column is a pivot column. So there's no solution in solving this except setting lambda to 0. And they conclude that the vectors, they must be linearly independent. That's a quite easy way to see how, or to check if the vectors are independent or not. So remark, consider a vector space V and K linearly independent vectors B with M combinations. They use the letter B for basis, I would say. And what they're saying is you can combine these basis vectors and scale them each differently to basically get a new vector. And you can do this m times. And now they're doing basically defining B as a set. Maybe it's a set, maybe it's a matrix, I don't know. No, it's a matrix whose columns are linearly independent. And what they saying is that you can construct a vector J so that you just multiply that matrix A with this vector lambda J. So you do a matrix multiplication of basis vectors, a basis matrix maybe, and a new vector, which is lambda, to get a vector X. And they want to test if this new set of vectors are linearly independent or not. So what they're doing is they take all these vectors, all these x's, they sum them up, and they put a new scalar in and check if it's still a null vector or not. That's what they're doing here. So now is the trick, I guess. They say this new thing, because it's a null vector, has to be the same as if you do this, because it's x, right? You can just replace that x with the b lambda j. Then they factor out the matrix, they move it to the left, and then they do a vector, what is it? Vector multiplication. Lambda is a vector, we know that because of this one. And that other scalar has to be a vector too, right? No, it's not. Or is it? No, it has to be a scalar. Because if it's not a scalar, then this would be a single number. But it's not a single number. It's a vector. It's a null vector. That means if this one is a vector, the x, then this has to be a scalar. Which means that this is still a scalar and this is a vector. Now what they're doing is they conclude that the set of vectors are linearly independent if and only if the column of vectors, in this case lambda, are linearly independent. I'm not fully understanding this. Let's do it again. Okay, so we start with everything which is independent. Okay, we know B is independent. Here B is independent and B is independent. So if you have independent vectors, for example, this is 1 and this is 1, B1 and B2. Now what they're saying is they want a linear combination. Let's say K is 4. For K1, not k1 but x1. For x1 they say we have lambda 1 1 b1 plus lambda 2 1 b2. Then we have x2, and then they say lambda 1 2 b1 plus lambda 2 2 b2. Let's make it a bit easier, just k3. Then we have lambda 1 3 b1 plus lambda 2 3 b2. So you will have three different x values, x vectors. So you have, let's say, this one is the red one, and that one is the yellow one, and the third one is the green one. Okay, we know that B is independent, but now what they're doing is, instead of writing this that way, they say it is easier if we write it like that. So let's write it like that. They say xj equals to b. We have b1 and b2. These are two columns. And then they multiply it with the vector, what is it? Lambda vector. Okay, in our case, we know that the B matrix is 2 times 3. I'm not sure what lambda is here. I can see that we have 6 different lambdas. But this cannot be 6. That cannot be right. Because if this is 6, then this would be a 6 times 1. And this is not something you can multiply. This has to be a 3 times 2. Oh yeah, I forgot here. I'm getting it. We have the j here, which means that we are looking only for one row. And for one row, in this case j, we have two numbers. Okay, there's another mistake. Just found that if k is 3, then we need to have also 3 b's. But we don't. We only have 2 b's. That means in our case, k is 2. That will reduce the equation to only 2. The green one will go. And then we will have the blue one here, something like that. So we will have here now 2 times 2 and 2 times 1. This will result in a 2 times 1 matrix. And we will also have, how many linear equations do we have? Linear combinations? M different combinations. Oh yeah, that makes sense. So if we say m is 3, then we could actually have another one. We could have lambda 1 3 b1 plus lambda 2 3 b3. That makes sense. Yeah, okay. Got confused with the k and the m. Okay, we have 3 different axes. And what they're saying is we can also write these 3 axes as kj. Okay, that makes sense. Now, what do we actually want to say? We want to say that, okay, what I'm not getting is this one. It's not clear if it's 0. They want to test it. They say, okay, let's take all these kj's, and if we do a linear combination of all of those, let's check if we get a 0 or not. Ah, I see, okay. So in this case, we have these combinations. Then they swap that out, x out for b, and lambda j. Then they move that out. And basically what they want is that that is 0. Okay, let's try that. We know b. In our case, let's just put the numbers in for b here. And then we have something like this. Yes, okay. And that block will be one vector. And if it's one vector, and we multiply that vector to that basic or basis matrix, only if that vector is linear independent, we will get a 0. And that's what they're saying here. Because we have this equation, they're saying that x is linear independent only if lambda is also linear independent. If it's not, then it will be not 0. I hope I'm making sense. Okay, so the last sentence here is, in the vector space V, m linear combinations of k vectors k1 to x1 to xk are linearly dependent if m is greater than k. Yes, okay, so if you have here, m is the number of equations, or the number of x we have here, this one, this is m, and k is the number of base vectors. If we only start with 2 base vectors and we go and produce 10 x vectors, let's say, then these 10 cannot be linear independent because we constructed all of those 10 with 2 input vectors, if you want. So that means that at least 8 of them, they have to be at some kind of redundant. So they have to be a linear combination, which makes them linearly dependent. They can only be linear independent if they're also only 2. And then they have to also constrain this, this equation. Okay, yeah, makes sense. Okay, so we have one more example left. Let's do that. Consider a set of linearly independent vectors b1 to 4 in Rn space. Okay, what they're doing is now they construct four vectors and they scale b's up and down. Now the question is, are the vectors x1 to 4 linearly independent? Okay, and the interesting part is that b, the base vector, is of Rn. That means it can be like unlimited in dimensions. It can be like 1,000 or million or 100 billion, or like basically there's no limit. So we cannot use b in that case to calculate it. We have to use like an abstract way. And here what they're doing is they just take the scalars, in this case the lambdas, and then just put it in the what they call the column vectors. Here, this one is this scalar, that one is that scalar, and so on. No, that's wrong. Other way. This one is here, that one is here. Okay, yellow in this case is, if we take example from here, I think only this part is important. So we have our b's like here, and they construct our x values. And we have the same question, right? Here. The x1 to xm are linearly independent if and only if the column vectors lambda 1 to m are linearly independent. So what is now lambda? Lambda here is, this is the column vector. These are now the yellow, blue, green, and red. So what they're doing is, basically they have to calculate the pivots. So they take that matrix and they bring it into row echelon form. And then they check if it's a staircase. In this case, it is. And then they say, oh no, it's not. It's not because that one is not a pivot. This column is missing a pivot. No pivot. No pivot. And now they're saying that x4, well, basically that the whole system is linear dependent, as we can express x4 as a linear combination of the first three. Exactly like that. Okay, so basically we learned that we can use the Gaussian elimination to check if two linear combinations or a set of linear combinations are linear independent or not from the first one. Given the first one is linear independent vectors, then you can basically construct a set of new vectors. If the set of new vectors is bigger than the base vectors, then it is always dependent. So it has to match, in this case 4, 4. And then you can ask, is this independent or not? What you need to do is take the column vectors, do the Gaussian elimination. And if you have one column which is not a pivot, then you know, okay, you can actually express that column as a linear combination of those columns before. Yeah, that's quite important as we want to understand if we have like redundancy in our vectors or not. All right, so thank you for watching and we will see each other next time.